Welcome to the Trend Detection Podcast, powered by Siemens. And now your host, Niall Sullivan.
Hello everyone, and welcome to this episode of the Trend Detection Podcast. As you can see, it's a slightly different episode. So we've got two colleagues on rather than one, which is really great. So we've got a really interesting discussion all around harvesting the value from data and the do's and don'ts and highs and lows. So that gives us a lot of scope with this topic, I think. So before we get started, I'll ask my colleagues to introduce themselves. So let's start with Chris.
Yeah, thank you very much, Niall. So my name is Chris Smith. My role at Senseye is to look after the best practice for deploying our technology into our customer base. So effectively looking at how you deploy predictive maintenance software powered by AI into a real environment. And looking at all aspects from connectivity, the people who are using it, and fundamentally the data that you need in order to achieve it. So that's myself, hence I'm here on the podcast.
Hi everyone, my name is Johnathan Bonner. I'm the head of solution engineering for Senseye Predictive Maintenance. And really, our solution engineering team, we are the technical advisors pre-contract. So we help our clients understand how predictive maintenance is going to affect their maintenance practices, but also help them to assess the right assets, the ones that will give them value, the data that is required, the infrastructure necessary to push data through to the cloud, the resourcing for the project, as well as success criteria. So very happy to be here.
Thank you. And thank you both. So I guess to get started, let's start with an open question. So why are we here? And why are we talking about data in particular? What's so important about data and predictive maintenance?
Well, from a pre-contract point of view, we really need to understand what a client has existing already. When we're trying to assess how effective predictive maintenance can be, we really have to assess how much good quality, useful data does a client have already, and what is their appetite for getting more of that good quality, useful data for the project.
Yeah, and I think fundamentally predictive maintenance comes down to the quality of the data that you have. Without a specific target, application or the data that you have showing you something. It doesn't matter how good the software you have, the pipelines you have, the people you have. If the data that you have is never going to show you anything about your assets, then there's nothing going to happen. So I think that's key to. I think these are all key, but I'm very much concentrating on data today. So.
Absolutely, and I remember one of our colleagues saying when I first joined that this isn't machine magic. If a trained condition monitoring engineer couldn't see the deviation, see the signs of degradation within the data, the application won't either. So really, it needs to hold within it those key signs of degradation to be able to show you the results.
And it's good we're focused on that, because I guess we talk about a lot focusing on utilising existing data, and why is that so important, or why is that beneficial? I guess maybe it's obvious, but it's good to spell these things out.
I don't think it's necessarily is an obvious point, because it comes up regularly in our conversations. So if someone says condition monitoring, they will instantly say vibration, and that's not an incorrect answer, but it's not necessarily a full answer. So traditionally you want to do condition monitoring, you can use vibration data, you have ISO standards at certain thresholds, etc. And that is a starting point, and that is exceedingly good at bearing faults, for example, if you've got a fault with your bearing. But machines fail in many different ways, not just the bearings failing, but you maybe have issues with windings in the motor, you may have pump pressure issues, etc. Now, what you could then say is, okay, well, we have all these potential failure modes. But if you already have existing data within your environment that can tell you about these failures, maybe not as advanced, but maybe advanced enough for you to take action, then you can save a huge amount of investment in adding specific sensors for these failure modes, when you can get something that allows you to start the workflow that you need in order to find the fault. So as an example, if you have a robot arm, what you could do, like a 6-axis robot arm, you could invest in 6 vibration sensors per robot arm. But let's say you had 1,000 of these in your factory. That's suddenly 6,000 vibration sensors, and that's exceedingly expensive. However, you already have the control loop system there. So why not grab the torque that comes off that? Because if something's starting to take more effort to move that arm, it's going to require more torque. That gives you that starting point to say, if you start to see that torque increasing over time, then maybe you need to start doing an investigation as to what comes next. So yeah, we really like to talk about using existing data in your environment, because there's a lot of things you could potentially mine there and save yourself in the long term from a financial perspective.
Yeah, but it's also not only the cost of the hardware itself. There's also the time it takes for installation. Any production facility will have production targets. So to find time where you can stop a line for a few days or a weekend or even a week, and install sensors, get the cabling installed, the trunking together, the PLCs gathering the data, whatever layers it is that are added onto the sensor. All of this takes up production time. So an installation that could take a few days, maybe a week, now gets spread over 6 months. So before you can start getting value, you have to wait 6 months to fit in with production, to get the sensors installed and to start collecting data. Whereas if you leverage your existing infrastructure, the data that's already there, you can start getting value immediately, or near immediately anyway. You are helping out your maintenance and engineering teams, giving them value from existing information. And yes, still install the additional hardware, but use what you have first. I think that's always been our standpoint. Let's leverage what you have existing on site first, and then we can look at additional hardware, additional sensors, or additional data streams once you're getting value from the project.
There's a certain irony in it as well of if you're wanting to increase the time you have to produce your product that's providing your business value, by installing a product that is going to reduce the amount of downtime you have, you need to then invest more downtime in order for that to achieve. Now, if you've got maintenance windows, that's fine, you can do it, but it's that time that you're losing, that opportunity cost. There's also the other big element of using existing data as well, is unlike a lot of kind of traditional threshold-based systems that are very reliant on kind of ISO standards and your operation of your machine being relatively consistent. A lot of modern production systems are expected to run very varied production cycles depending on the product, depending on the demand. Maybe they need to run faster some days, slower, different products, etc. That information is key for understanding the rest of your data as well. Even if you did go off and install vibration sensors or current or pressure, whatever it might be, if you haven't got a understanding of the existing data that you have that can tell you what your production is doing, then you're limited in what you're able to see. As a big example, if you're running fans, and we've had this a few times, so you're running fans and you're asking the fan to run at a certain RPM, but it's not responding, traditional threshold system's not going to see that, because you've asked it to change and nothing happens. Whereas if you know that within your in the predictive maintenance program, you're actually taking into consideration whether it's running or not running, those kind of things will pick out. You'll see that you've asked it to do X and it's not doing it. So there's actually a fault on that fan. And that data tends to already exist. So why fit ways to look for that when it's already there?
We should also point out exactly what we mean when we're talking about data for predictive maintenance. So really, there are 3 forms of data that we look for in any environment. The first is condition monitoring data. So this could be pressure, current, torque, vibration, temperature, speed, flow, cycle time, a full range of useful data measures. And within it, the important factor is that within that data, you need to be able to see key indicators of degradation or failure. So meaningful change indicating failure. As Chris touched on a moment ago, there's also operating context that we look for. so that the application can build an understanding of normal operating change and reduce the amount of alerts just because you've changed the speed of the motor, for example. So this could be speed when you're looking at a variable speed drive. In FMCG or food and beverage, for example, where you have different, let's say, size bottles running through the same production line at different times of the week, having an indication of a product change is important, because then you can build up an understanding of what normal is throughout these different products. And then the third form of data that we use is maintenance data. So that can come from an on-site maintenance management system, or CMMS, or you could add that in manually into the application itself. So those are the kinds of data that we find useful and that we look for in any deployment.
I was going to say, within those types of data, though, it's also about quality as well, right? So what sort of issues in terms of data quality do you both sort of encounter on a day-to-day basis?
So I think within that quality element, there is quality and also suitability as well. So I think from quality perspective, the biggest problem we tend to face is the sampling rate of the data that you receive. So depending on the team that you're working with, but there's a general view of more data is better. Especially in this kind of not so much now, but for the past few years, there's been this kind of whole big data element where people say if you get lots and lots of data, you can find really interesting correlations and patterns, etc., that can tell you about what's going on in your environment. In reality, predictive maintenance is much more of a small data problem, and therefore you're doing large analyses across multiple measures. Well, actually, you've only got a limited number of measures on an asset, unless you really break the bank and really put as many sensors on as possible. You may only have 5, 10, 15 different kind of measurement points across a fleet of assets, never mind just one. And so one of the big issues in that kind of big data thing, it's about getting hold of the data and not really considering how you sample the data. So perhaps you're running a steel line that produces a coil of steel every hour or whatever it is, and it goes through a whole production point within that hour. And then you just say, okay, well, we're going to sample this data every 5 minutes, just completely independent of whatever is happening in that process. Just every 5 minutes, take a reading. Or vice versa, you've got an entire very quick system, like you're making contact lenses, where your machines are moving very quickly using servo machines. If you're then taking a sample every 5 minutes, in the first instance, you may be missing key points within the production cycle. In the second one, you're definitely missing key points. If you're just taking it at random or at a set point, sometimes the machine might be at point A, sometimes it might be at point B, maybe it's not moving another time. And that's one of our biggest challenges, is trying to make sure that the people we work with are thinking about how are they collecting that data. Now, the other extreme is people then go, okay, we're going to sample at an extremely high rate, milliseconds, or even, well, now and then nanoseconds. Most of the time we get, okay, well, we must sample at milliseconds. But then you just got a huge amount of data, a large data volume, without any suitable data in there. So what we looked for is something called a condition indicator that Jonathan mentioned earlier, but specifically in terms of data quality, is something that if that were to change in the absence of known stimuli, so in the absence of a change in production or a change in product, a change of that is an indication that the condition of that asset is changing. So in a sample where you've got something moving from point A to point B to point C, then it picks something up and then carries it here and then comes back. Actually, sometimes the most suitable point to get the highest quality data about, say, the motor that's running that system is to take the current when it moves from the last point back to home. And so, yeah, trying to turn large amounts of data into something that's actually meaningful for the health of the status of that asset is one of the biggest challenges of data quality.
Also, understanding where the data is sitting, which part of the infrastructure the data is when we start off our investigation with our clients, we look for many layers of the infrastructure. So, do they have smart sensors? Are they making use of edge technology? Do they have access, or is their data within PLCs, drives, inverters, SQL databases, factory historians, cloud replication services, additional cloud storage historians? Where is all of this data sitting? So there is the capability of the system, or the piece of infrastructure where the data is, but there's also the skill set of people on site. It's all, you may have the perfect system, but no one who will know how to process the data, downsample it, make sure that the data is being sampled at a return movement, or at the right frequency, or based upon a trigger. So there's a number of assessments you need to do around where the data is sitting, the capability of that system, and then the personnel capability to turn that huge data set, where data is being stored at a millisecond rate, but to process that down into useful key indicators. I quite often use the example of current for a motor. Current is most typically found with being stored within a PLC. That data will be stored at a millisecond rate, but we're not looking for that. We may want it as a minimum, maximum, and average value every minute, giving key indicators of that current profile over a minute period. And also, by getting those key indicators, I'm tracking those, but you're heavily reducing the amount of data you're sending to the cloud. So, again, assisting with costs.
Yeah, and it's been one of my personal big focuses is trying to reduce that barrier to predictive maintenance by working with our product team to look at, we go through several implementations of our product, and deploying PDM. And one of the big challenges is getting the right data to us. And we're constantly working with product to move that barrier. It used to be that we expected our customers to be able to do all of this. Well, we've been focusing very much about, okay, let's remove the need to pick out the interesting parts in the data. So we have something called derived measures to do that now. Customers have higher frequency data. Well, they don't know how to downsample it. Okay, let's try and reduce the frequency at which we ingest data as much as possible. So this is something we're always working on to make it as easy as possible, and make this challenge of making the data of good quality for predictive maintenance. But there is always going to be some element of it, as Jonathan pointed out. Because the pumping huge amounts of data to the cloud can be very expensive.
So, Chris, I'm going to ask you a question now.
Sure.
Can you give us an example of a huge data set that you were given from one of the clients where it looked promising, but actually on further investigation, it wasn't that useful? So maybe too much noise within the data, no context, something along those lines.
Funnily enough, typically if we see a large data set, if we're sent gigabytes of data, that's actually when our heart sinks most. We'd much rather something that said 1 megabyte maximum, because when we have that, it's a case of someone's really thought about the data they have, or they have quite a limited data set. So generally we see large data sets sent to us. You're having to think of really interesting ways to get it to us so we can analyze it. And then we spend the first day of looking at the data of scrapping 95% of it. It's typically rather than thinking of a specific example, I would say the process that we go through is within a large data set. Really, what we want to try and achieve is look for those condition indicators, so that when we know from a physics perspective that, or an engineering perspective, that if you're tracking that data over time, it's going to show you about failure from a fundamental perspective. So not even necessarily that there's failures to be able to show that, although that does help. And so when we look through this data, we just look for anything that is, say, things like current, torque, pressure, differential pressure, that kind of thing, that kind of information. We'll then look to plot that or kind of visualize it in some way to see what changes we see, maybe over a week or a month, because that is likely to be due to some sort of production. And then we'll look at we then have a discussion with the end user, or the customer or the client, or however you want to frame them, about, okay, what is happening there? It's step changed at this point here, and it does it every week. What could that be? Oh, and you find out, oh yeah, we run the line a bit faster. Okay, do we have a tag in this data that is the kind of the speed for that line? Oh yeah, we've got these 3 potential ones, but actually we only need 1 because all we need it to do is understand that change. And so we can then and that's what we're looking for. So when you imagine when you get huge gigabytes worth of data, that's a lot to trawl through in order to find that information. We'd actually rather start small, maybe with a week, with the things that we probably are going to monitor with a few, and build the context up. And then at that point look at a longer data set if you've got failures in, etc., to look for those to validate what we've seen, but also show how start kind of feeding that into the application to get the value from that. Hopefully that answered your question, Jonathan.
Good question. Maybe you should have my job. But I was going to sort of add on to that as well in terms of the sheer amount of data, and data can be spread across lots of different systems as well. So I was just wondering what sort of the challenges of bringing that data together are as well.
From a pre-contract side of things, when we're evaluating multiple systems, again, it does rely on the capability of the layer of infrastructure, the system, and the personnel capability, because those are, from our experience, or at least my experience, those can be some of the most challenging. But then you also need to look at communication protocols. How are we going to get the 2 systems talking with each other? People may say, yes, we can integrate through MQTT. Perfect. But there is no standard for that type of communication. So although the 2 systems may be MQTT enabled as far as a protocol, they are not set up to talk to each other. So you need to start thinking about the actual logistics of getting data from one system to another, at least before the contract starts.
And this was something pre our kind of Siemens life, as it were. So when we were Senseye as a software manufacturer, software product business, thank you. This is where we would be like, okay, off you go, Mr. Customer or Mrs. Customer, or you work out how to do that bit or get a third party in, etc. And we're kind of beholden to the success of that deployment. Now we're part of the kind of wider Siemens network. Then there's something that we can now work with other teams within Siemens to be able to solve that problem. But it is still something that requires, as Jonathan said, it requires a lot of thought of like how are you going to get this from A to B, and how are you going to do it reliably as well. You want it to be without it taking forever to build. So there's that one of those kind of triangles of effort to work out of getting the data there in an efficient manner, which is also reliable.
And I would say some of our best projects have come from clients who've tried IoT initiatives, Industry 4 initiatives before, PDM projects before, and have failed to an extent because they have learned the hard way the right and wrong things. They've also done a lot of pre-work in understanding the types of data that they'll be wanting to capture and store. The sampling rates of these, the communication protocols, the people required. They understand that projects don't just happen overnight, that it takes, especially in the initial stages, the evaluation. And I think, Chris, you're probably best to speak around how we do the first few steps of the evaluation from our methodology. But, they've gone through all of those troubles before. So they are much better prepared and better set up for this new project. They understand that in the initial investigation, the initial setup phase, but up until getting data into the app, once we have that, all of that work before then is more intensity of efforts from their side. And once data is in the app, actual use of the application, their day-to-day or weekly efforts heavily reduce.
I'm going to steal Niall's job this time, so it's my turn to try my hand at this. But Jonathan, what do you find is the biggest misconceptions that you see? So I think you talked there about the people who have done projects like this before, that they know. But what about those who are a bit more green to the field? What are the kind of general misconceptions around data that you see? Because you filter that all out by the time it gets to me. So.
Yeah, I think one of the biggest things that I get is, oh yeah, we've got data. Don't worry about it. It's there. It's over there. It's good data. And when we actually start to evaluate what it is, it's maybe process related or unrelated to the condition of the machine. Not to say that we can't use process related data as either indicators or for monitoring itself, but that's not necessarily the core source of truth we try and go for. And then I would also say one of the biggest things that we have to field almost all the time is around the people factor. People saying, okay, well, that's fine. You come show me what you can do. I will give you my data. You show me what you can do with it. And that's not how projects succeed. A predictive maintenance program, project, initiative cannot be run as we come and do something to your environment. It has to be done as a collaboration. I like to think of it as we're not a provider, we're a partner. We're not going to provide you something. We're going to partner with yourselves, partner with your teams, take you on this journey, show you the way, inevitably show you how to do it yourself, or the setup and so on, together, because that's how projects succeed. So when that comes to getting data, we don't typically send people on site to go and interrogate PLCs, to go and get exports of data. That has to come from the client. So you have to give them training and understanding of the type of data we're looking for, just the file formats that we can accept for our initial evaluation and so on, but really taking them on the journey through predictive maintenance.
Yeah, I think part of that is an enablement as well. So for a customer to understand what's been done to their data, or how it's been used, and so that they can see when they do get an insight, a case. So a case is our active notification system. They understand the root of it, and therefore they understand what that can't do, what that can't tell them, but also what they can do, what it is able to tell them. And if they've understood how it's used and how it's gathered, then that can give them much more value. Because one of the big things that we work through a lot is understanding context. We keep coming back to this, but what we don't like doing is being a vendor. We want to be a partner. If you had lots and lots of false positives, that we're not satisfied. That's not our bag. We don't want to just deploy and run away. We want you to have a successful deployment. And one of the big things of that is to be able to communicate with the customer to understand what their machine's doing, in order to that might explain some of this away, because we can handle that. We can make changes to the algorithms, and then suddenly the number of cases you get massively reduces, and the chance of value massively increases. It's again back to that people thing. People want to look at 5 things and 3 of them be useful, rather than 50 things and 3 of them be useful. The only way we can do that is in a kind of partnership model, and it's about highlighting that we might be the experts in our application and how we handle that data, but the end customer is always going to be the expert in how their machines operate, because that's all we're fundamentally doing, is trying to understand how machines operate and converting that into data to analyze. We're not doing it, there's no magic there.
And Chris, do you want to run through how we get to a point of saying, all right, this is the right data, this is the right format, our process for doing that?
Yeah, so I think I touched on it earlier, but it's effectively, we want to look, what is your machine? Is it pump, motor, etc.? And actually step back from that. Often we get given, here's a press machine, or here is a cold mill rolling process, or this is how we make glass, etc. To us, we're definitely not experts in how to make glass or steel or whatever the material might be, or cars. But what we can do is the first thing we look at is, well, fundamentally that big machine is actually made up of several components of smaller machines. So the first bit of data, as it were, in that scenario is how do we break that down into its constituent parts so that we know what we should be monitoring. So actually, it's not your press machine fails, it's the motor that runs the feeder that fails. That's actually what's failing. And so let's monitor that. And we go around and do that. So that's the first stage. And then when we understand what this equipment is, we look at what is your existing data that you already have. Maybe you already have sensors. It's funny how many times people discover they have sensors on things that they didn't realize, because some past project was done, no one recorded it, and they're just hanging there with a cable hanging out. Or also what's in their PLCs. And we look at that to think, what is going to give you value, what is I wouldn't use. And then we talk with them to understand what the process is. So is it continuous line? Is it discrete manufacturing? In order to understand what we might need to consider. Most of the time it's machine speed, and in fact 95% of the time it's whether it's running or not running. That's actually probably the biggest one. Because that matters, I think I mentioned earlier about the fan scenario. If we know if it's running or not running, that's a lot of information we can know whether it should be doing something or shouldn't be. And then once we've kind of gone from that engineering approach, then we just make sure the data makes sense. So we make sure that it is sampled at a sensible rate, so that it can capture everything that happens in the cycle, or we can look to simplify it, to look for when there's no load and it's returning to home, something like that. And then we make sure that they can actually get it to us. So those conversations tend to be quite separate, and then come together at the end. You don't have to do this in series; you can do it in parallel. But what we do in that whole process is communicate with the customer, show them what we're doing, so that actually when they come to want to onboard 2,500 assets in year 2, they know exactly what they're looking for because they've gone through it several times, and actually that can speed up the whole process. You're not reliant on us having to understand all your equipment in your environment. You now have the tools, the capabilities to be able to go, yep, here's my new machine, I need A, B, C, D, E, F, and I need to consider G, H, and I. This is where I got my alphabet wrong. Check afterwards. Off we go, let's onboard it.
I agree. I was just thinking, actually, as we've talked a lot about sort of existing data, but not about what on the other side. If you have everything in place and you work in collaboration, like I said, it's not just vendor-client relationship, it's very much teamwork. But if you get those elements right, what are sort of the opportunities for customers, in terms of what they can achieve with predictive maintenance?
Go for it, Jonathan.
All right. Well, it really, again, it goes back to the quality of data, the type, the fidelity of data that you have. Let's use vibration because it's the perfect example. If you have a basic RMS vibration value, that the RMS vibration is effectively telling you about the power in the component that you're monitoring, the bearing and shaft and loaded areas. It's just telling you about the power, but there's very little detail around what exactly is happening. Whereas if you had more specific indicators within that vibration, so let's say when you now start enveloping frequency bands, so from 0 to 100 hertz, 100 to 500, 500 to 2.5 thousand, 2.5 to 12,500 hertz. Enveloping of those are going to give you key indicators of types of failure. So your 0 to 100 hertz will tell you about misalignment and imbalance. So you could look at a peak to peak and an RMS value, or a peak and an RMS value in that frequency band. When you start to see changes, you can nail it down to either misalignment, imbalance, so on. Anything a little bit higher, so your 100 to 500 is you're now starting to look at rotating looseness, maybe soft foot, that type of thing. When you start going into the higher frequencies up to 2,500, that is very late stage bearing degradation. And your 2.5 to 12.5 kilohertz, that is early stage bearing degradation. So now, again, you're still not sending huge amounts of data, but you now have key indicators within that. And then if you were to get amplitudes at various frequency points, so your 1 times running speed, your 2 times and 3 times running speed, if you could get key indicators around your bearing frequencies, you can then start to be very specific and say, well, this is indicative of your outer race bearing, of an outer race bearing defect. So you can start becoming very specific. And I'd say that's the same with all other data sets that we would look to use. So the better or higher fidelity sensing or data quality you have, the better you will be able to predict. But quite often we find that current, torque, and speed are everything we need to monitor a motor. You can be very successful with very basic measures. But again, if you want your teams to know exactly what is happening, then you would need to invest in higher fidelity sensing. So within the application, we can add in potential failure modes and recommended actions based on previous learnings, previous failure patterns that the application has observed. With higher or better quality data, that messaging can become a lot more specific. So instead of just saying potential failure modes could be bearing degradation or misalignment or imbalance, and giving a list, you can then start to be very specific around what the potential failure mode is and what your mitigating action, your work event should be to fix the failure.
And I think that's a really good point, because it's one of the biggest misconceptions we have to people who come to a project later, potentially, so who have not necessarily been involved in the whole process. Maybe they're a new hire, or they've come from a different department, whatever it might be, and they join the predictive maintenance and say, okay, please tell me exactly when this bearing's going to fail and how. And I said, well, we can't. And I said, well, you're the predictive maintenance guys, we send you vibration, or we send you current, why can't you tell this? I said, well, fundamentally that data will never ever tell you that kind of information, because it just doesn't exist in that data. It's a bit like when you could see it as if you invest in the lower end vibration sensors. It's not like a person that you send your car to the garage and who does a full diagnostic to find out what's wrong with your engine. It's much more like they check the engine light. This is a really good example that was provided by one team I work with. That's not to say that check engine light is not valuable. If you didn't have that at all, you could be driving along quite happily, and then suddenly the engine falls out the bottom of your car. That's pretty bad. Equally, you could invest a huge amount of money in having someone literally test your car every single day to see what's wrong with the engine, but that's going to probably cost you more than the car itself. So there's a balance to be had, but then it does give you that risk of misconception of, well, you have vibration, therefore you can do this. And that's both to show the opportunity, but it also shows one of the risks about just saying you do predictive maintenance with vibration, for example.
Yeah, and also, because the application is monitoring hundreds of thousands of bearings at the moment, doesn't mean that your bearing, your vibration relates to any one of the learnings, any one of those 100,000 bearings learnings that we have. When I was a condition monitoring engineer, I saw assets that had extremely high vibration on them run for months. They were well above any ISO standards limits. It was completely within the red. We thought the bearings were going to fail, the drive shafts were going to bend, it was going to completely destroy the machine. The maintenance teams didn't do anything about it, and it carried on running. So, there's no way to predict something that doesn't have a definite lifespan. Something, you could have a small bit of vibration starting now and it could fail tomorrow. You could have something run at extremely high vibration for months. All you can say with certainty is that something is changing and that you should plan it in.
We see this all the time with we have to be really careful about what we compare to what, and what we say is what, and that's why we focus so much on looking for change rather than like levels. We can put thresholds in and forecast, etc., but we like to look for change, because that, whilst it might not tell you when it's going to fail, unless we have a very, very well matched failure from something else, in which case we can give a good indication. but the environment is going to affect that data. The where it's connected to the floor is going to affect that data. We've seen that with equipment that on the bottom floor is connected to a concrete floor. Same equipment as on a second floor is on a steel frame, completely different vibration levels. Or totally different locations where a robot arm fails in very quickly in one environment in a very particular way, does a very kind of typical trend step and then fall off. In a different environment, it's a really slow trend over a long period of time, because it's one of them's in a temperate environment, one of them's in a desert. So you've got all these elements that you've got to try and consider, and you could instrument about. But actually, what we want to do is say, look, this is changing. If we can, we'll characterize what it could be. But if it's changing and you're not making any changes to that asset is becoming less performant, is moving towards some sort of failure, we'd suggest go investigate. And I think that's interesting because it comes to that high and low element of, we're seeing this potentially with the Chat GPT era. There's this huge potential hype around what it is going to do. People talking about it's going to completely end the world. Much like a lot of this new technology, I think predictive maintenance is further along on the cycle of the hype cycle of now it's a bit more like we're moving into the business as usual. But there was a kind of a dip of, this isn't going to tell me within 10 minutes when the 10-minute accuracy of when this asset's going to fail. But that doesn't mean it's not valuable. In fact, people are getting huge amounts of value knowing that their assets are starting to fail, that they can plan well in advance to find out what the problem is and do something about it before it stops their production. And that, I think that's where we're in now. Different people are in different areas in that kind of cycle, but I think that's what we can do with the data, and that's still valuable.
Yeah, I remember getting asked quite often. Okay, well, we were asked/told that we're looking for a system that can predict remaining useful life with 2 years accuracy. It's 2 years in the future. Now, and that had a lot to do with market maturity and misled expectations. Why would you want to know 2 years in advance that your asset's going to fail, and be specific around that failure? The further away you are from absolute failure, the less specific you can be around what that failure is, first of all. And secondly, what is the point of leaving an asset to fail for 2 years? Really, what you want to know very early on is that something is changing. With enough time and with enough specificity to go and investigate the right asset, the right component, the right area, you'd want to know that the drive end of your motor is where you should be investigating, not somewhere in a press. But you can go and investigate, you can go plan in, make sure you have the spares, the right resourcing, you can plan it in when production requirements allow, and you can go do something small. It's a lot easier to grease a bearing than it is to change a bearing, and then, have to redo a completely destroyed machine or a completely destroyed motor. But that's really what the point is. It's not about knowing specifically that in 2 years' time you're going to have a bearing failure. But early on enough to know, okay, there's change in this bearing. Let me go and grease it and see if everything returns to normal. And if it doesn't, well, then we can plan in the replacement.
Yeah, and I think we're very much looking to make life boring, I suppose. It's not capturing. Maybe sometimes it is. Sometimes you capture a thing just as it's about to fail, but in reality, we want that exact scenario. A little bit of a change. I'll go have a look. The lubrication's a bit low, or it's slightly misaligned. Okay, we'll just get that corrected. Suddenly you've added X years of life to that asset. Whereas if you left it, even if you get in before it fails, you may have to replace the whole thing, and that's much more costly and wasteful, especially when we're considering the environment much more in the space as well. So it's those small changes. And I think that might be one of those high and lows scenarios. I think the other one would be, we've talked a lot about the project, about the deployment, about getting things up and running. And you're up and running, you're monitoring equipment, and absolutely nothing happens for 4, 5, 6 months, 12 months, whatever it might be. Because all your assets that you're monitoring are fine. And we do get the odd conversation and where people say, so you've been running for 2 weeks, where's all the value, where's the avoided failure, etc. So, well, nothing's failing. And to our kind of more mature customers, that's actually where they want to be. Nothing's failing because they have everything under control, and in fact they know that everything's in control. So it's not just that it's in control, they know it's under control. And so now they can plan accordingly their maintenance. No longer do we need to do that 3-month grease sample that we do, which is costing us a fortune because we're using a third-party vendor to do it. Or it's no longer are we changing all these bearings out because we were told by the manufacturer to do it, because actually they're absolutely fine because we're confident of the data and there's no change. And so, but there's like a threshold of which to get to that point where you kind of need people to believe that the application and predictive maintenance as a whole is doing that. Unfortunately, that is tied around a real event, a failure that actually happens. And unless we often joke about getting a hammer, getting on a plane and maybe hitting something where no one's looking to make it happen, but I think that'd be professionally a bit dubious. But we're waiting for that. But actually what we really want to happen is you get into that second part where you're doing bankable value, avoiding unnecessary maintenance, avoiding unnecessary usage of spares, and you just accumulating value. And now and then you get the nice big win. Fantastic. It keeps reminding you why you're doing it, but that's not necessarily the biggest value that you'll get.
Actually, in fact, Chris, you're completely right. The value that you can harvest from your data is actually about acting on the information. There's no point in waiting for something to fail because you don't believe the system. It's about actually using the information that is provided as a result of all the data you're feeding into the system to affect your maintenance practices. So to react when the application is telling you something is worth investigating and reacting to. Or not reacting when the application is telling you everything's fine. So your planned and preventative maintenance schedules before going and stopping an entire line for a week so you can do your planned maintenance. Have a look, see what the data is telling you, see what the application is telling you. Confirm that everything looks to be running perfectly fine. And in most cases, you could reduce the amount of replacements and the actual amount of time by half. In some cases, sometimes even more. If the asset is running perfectly fine, why would you change things up? But now that you have visibility of it, you can make better decisions. And really, that's what predictive maintenance is about. It's a decision support tool.
Yeah, and I guess so. Been really interesting discussion. So, like I said before, I don't think I was needed here. I'm just an interested observer between you. Maybe you should have your own show. We're going to talk about that later. But what I wanted to round things off is back to sort of the original question. So we're talking about harvesting value from data and the do's and don'ts. So just to finish off from both of you, just to maybe summarise the do's and don'ts of that exact question, harvesting value from data.
Well, I was gonna go from a pre-contract do's and don'ts, and then you could do it from the actual project.
Yeah, makes sense.
So before you start a project, do think about what it is you want to achieve. Think about what it is you want to gain value from, whether that's assessing the right areas, the right equipment types. It shouldn't necessarily be based on criticality, but rather around what is giving you the most trouble. Where are you spending the most amount of your money? Do speak to experts, people like us who are more than happy to guide you on the journey, and don't just think, okay, well, I'm going to spend lots of money gathering as much data as I possibly can, and then it will become useful later, because you will end up wasting a lot of money and a lot of time and a lot of resource for very little value.
Yeah, so I think do recognize the importance of the right data, not just in terms of from an engineering physics perspective, but also from a sampling perspective, like good data science principles of making sure that you sample at the right sampling rate to actually see things in the data. do, and actually we haven't touched on this, but do ensure that you have enough data across enough assets so that you can actually have a chance of seeing something within a reasonable time frame, whether that's 12 months or 2 years or whatever it might be. So don't focus on just having a small data set on 2 or 3 assets, because the chances of those 2 or 3 assets failing is relatively small. You're effectively rolling the dice. Give yourself as many dice to roll as possible. And don't be unsurprised if the value you're expecting doesn't come straight away once you're up and running. The project in itself isn't necessarily valuable. It is the usage of the application itself. We used to bang on about, we're up and running, we've got things going, we've got this data, etc., and really kind of celebrate that. And it's worth celebrating the wins. But actually now we're much more focused in that, okay, are you getting value? And sometimes it requires patience. So yeah, I think that's what I would summarize with do get the right data and don't be disappointed when it doesn't come straight away.
Fantastic. Good way to end as well. So I think that draws us to a close, but it's been a really interesting discussion. Thank you, Chris and Jonathan, for your insights.
Please like and subscribe on all major podcast channels and find out more about Senseye Predictive Maintenance at Siemens.com.